and I'm sure you all saved me for last for the most low efficiency subject today, which is GaN non-uniform distributed PA design. Just to give a little context, if you are able to achieve 25% power added efficiency across a decade of bandwidth, you're a hero. So that should give you a little comparison to the reactively matched and other advanced topologies you've seen today. So some background and motivation for designing these things in gallium nitride. Below 100 gigahertz, it's clear that gallium nitride is the dominant technology to get the highest amount of power out of a MMIC. Once you get to 100 gigahertz, you really transfer over to seeing indium phosphide HBT type designs is what the best high power and efficiency technology is. Now I realize we heard some talks earlier today where we're trying to push that limit with gallium nitride, but commercially today, I think you would say indium phosphide is king. But below 100 gigahertz, gallium nitride for sure. So the non-uniform distributed MMIC PA topology is the dominant, and I would argue the only topology right now that allows you to achieve something like decade bandwidth monolithically. And so this is showing a diagram of what a basic implementation of a non-uniform distributed power amplifier is, which is fully integrated. Now, there are differences to some of the distributed amps you may see commercially that you're like, well, I've seen stuff operate, for 100 gigahertz. Well, those don't have the bias keys integrated. So I'm focusing on a fully monolithic integrated solution, which is what you see here. So you have your basic input blocking capacitor to block the the gate voltages from the input. You have your output blocking capacitor to block the drain voltages from the output. This is just like a standard reactively matched PA. But then you immediately notice a big difference is you have a set of N transistors where you have transmission lines between each of those transistors on the drain as well as the gate side. You have these coupling capacitors to the gates, which serve to, one, block the gate voltages that are applied to the FETs from the termination resistor on the gate line, which we'll talk about more later. You also have these resistors to the gates of the FETs, which allow you to apply the gate voltage to the FETs now. In this common implementation, those gate resistors are effectively quite large to prevent any signal from coupling down those lines, and you certainly need to consider the size of them for some other reasons, which we'll discuss later in detail. But basically, N transistors that are all driven in very different phasing along the length of the gate line and delivering power to different transmission lines along the drain line. And if you do this all right, they magically add up at the last transistor and go to the output, and you've done a great job over bandwidth. So that's the reason you would do this. You don't do this for an efficiency reason. You don't do this for an output power reason. You do this for a bandwidth reason. And in my experience in gallium nitride, once you passed I would say an octave of bandwidth, I think Taylor mentioned that in the previous talk, then I'm under the impression personally I can do a better job with a distributed amplifier versus a reactively matched amplifier. Now, there are limitations on power, as we'll discuss here in a little bit, but that's where I see the breakover point being. I am showing up here 3 different implementations of what these transistors often look like in a MMIC, where you go from what I will say is the electrically best, thermally worst layout to the thermally best, electrically worst layout. So these are different implementations you can see in these FETs. And a lot of times you will use something in between, say the hybrid layout, where you're using in-source vias with gate fingers to another set of in-source vias to kind of do a trade-off where I want some good electrical performance so I can get to say 20 gigahertz or 40 gigahertz, but I need some better thermal performance because this is going to be a thermally challenged design in general. So one more thing to mention before we go to the next slide and start talking about how you actually make something like this is that another reason you like to do it is load tolerance. You see a lot of reactively matched amplifiers, obviously, but one thing that reactively matched amplifiers do is they load all devices the same, in the output stage. And so when you pull the load, you're pulling all the output devices in the same fashion. And if you pull them all to a very high dissipation region, you make smoke and fire and everybody's mad and you're in trouble. Well, the nice thing about distributed amplifiers is that they all get pulled to a different load effectively. You can think of it as a balanced amplifier on steroids, where, in that case, each half of the amplifier is pulled to a different region, or in this case, all end devices are pulled to a different spot. So it gives you even more load tolerance than, say, a balanced amplifier does. So I'm going to kind of walk through how I typically design these things, and what the things you have to think about when you're going to start designing a distributed amplifier and some technology. So the first thing you need to do is you need to know what the device performance is. You need to have some load pull data, or perhaps you have a nonlinear model which you can perform load pull on. And what you really want to evaluate is you need to know how much power density, at a minimum, how much power density you have and how much power out efficiency you have at a given load target. And so that's going to really be what restricts you. I personally think that since you're so thermally challenged in these designs because of the way the loads swing around, that you really want to try to design to the power added efficiency load when you do this. And so step one, figure out what your power density is, figure out what your RP and CP are from a normalized basis, so per millimeter from a standpoint of capacitance and times millimeter for resistance. And so you can also start to play some trades after you know those things. If you have that at a particular voltage, you can make some assumptions about how those scale with voltage. So as drain voltage increases, the RP is going to scale linearly because the voltage goes up and the current stays effectively the same, and vice versa. When it goes down, it will scale linearly down. Power density and optimal resistive load also increase, right, because of those things. And so what you do is, once you figure out, okay, I'm going to look at my trade in terms of what voltage I'm going to operate at, and I'm going to assume I'm operating into a 50 ohm load because that's what the entire world wants in terms of my output load, then you basically have your answer in terms of how much periphery you can use. And so that answer is your per millimeter RP divided by 50 ohms. So if I have a 100 ohm millimeter resistive load target for my power added efficiency load at my FET, I can use 2 millimeters of FET, and that'll give me 50 ohms. And that's how you do it. You don't get to do a lot of transformation like you do in, say, reactively matched amps, where I can just, I'll just double my power. I just need to transform the load. It's a little bit more difficult when you do it with distributed power amplifiers. So here's an example of estimating the FET periphery in terms of, okay, I have this technology. I kind of know at a particular voltage what the optimum resistive and capacitive load target are, and I know my power density there. So let's assume I can kind of scale around the drain voltage, because a lot of these technologies can operate over a pretty wide range of drain voltage in gallium nitride. And so in this example, I'm assuming an 80 ohm millimeter load target at a power density of 2.5 watts per millimeter at 20 volts. This is a very representative of 150 nanometer gallium nitride technology. The RP of 80 ohm millimeters is very much representative of a power added efficiency type load rather than just a purely, max power type load. And so you can see, as this voltage increases from, say, 20 volts up to 28, well, I can use a lot more periphery because my load target is going up, right? And so I can use more millimeters of periphery to get back down to 50 ohms. All right, that seems like a good thing if I want to get, if I want to get more power. And that's obviously true because I can use more periphery to get back down to 50 ohms. So that's one way I get more power. Second way I get more power is my voltage went up. So I get more power density for the periphery that I use. So it's like, well, seems like using the maximum voltage of the technology is probably the smartest thing to do if I want a maximum power amplifier. Well, there are some additional considerations which we're going to go through in a second, but one of those considerations, again, is thermal. As we push these voltages higher and higher, thermal becomes more and more of a challenge, and efficiency is also more challenge, as you will often see. So those are just some basic reasons why you wouldn't necessarily want to do that. So, but let's just say you've decided on a particular voltage that you're going to operate at, and you know how many millimeters now based on that voltage. Well, now you need to select the number of devices. And so the more devices you use in a stage, the flatter the achievable performance is going to be within the frequency band you're operating in. The periphery of each individual device obviously will be lower because your periphery is fixed. You're using more devices. Stands to reason that each individual device has a lower periphery, which can be a good thing from a thermal perspective. Another thing to take into account, design complexity increases substantially the more devices there are, right? So you got to figure every single device you have some gate line between them, you have some drain line between them, you have another degree of freedom when you're optimizing this design. So it's just something to consider. There are also diminishing returns to the performance at some point. I mean, if you use, say, 8 cells versus 10 cells, you can probably get, a little bit more performance with 10 cells, but I typically stop at 10. I have never seen personally the ability to achieve additional advantage out of going beyond 10 devices. So my personal recommendation is I would stop at 10 devices. But certainly, if you feel like going for more than that, then you should give it a shot, see what you can get. I mean, I don't want to restrict you. Another thing to note, and we'll talk about integrating a driver amplifier with this, say, output stage non-uniform distributed power amplifier, is the driver stage can often be implemented successfully with a lot fewer devices. So I've done them for different designs with as few as 3 devices, honestly, and that can often provide acceptable performance. But again, this really depends on a lot of specifications. So these are just in general thoughts to kind of keep in your brain as you're starting a design versus just hard rules. So in terms of estimating the individual device size, right? So we know how many cells we have now, and we know the total amount of periphery. So the first thing you might consider is like, well, let's just divide them all up evenly. That might be a really good idea. And so there's a good reason why you don't want to do that. And let's talk about that. So the minimum size for this first device, right? Q1. That's set by the maximum impedance transmission line, which you can synthesize over the broadband and the passive technology. So a reasonable assumption is around 100 ohms. Now, you can get a little bit beyond 100 ohms, but 100 sounds good for a presentation. So let's just assume that that's where we are. That Q1 is almost always sized at minimum periphery in NDPAs, as that device will see the worst case power dissipation. So you have kind of 2 challenging requirements right here. You can present that device with a 100 ohm transmission line, but you really want to make it small. So what's the problem with high voltage? Immediately you're like, okay, I want to make it small, but I need to get it down to 100 ohms. Those 2 things are in direct conflict, right? The smaller I make it, the higher I push my RP. So I have a problem there, and we'll talk about that more later. But honestly, that Q1 is one of the things you really want to do the best matching, because you will see in your design in gallium nitride, that's your problem device. That's the one that's going to see the worst amount of dissipation. That's going to drive your channel temperature, and that's going to drive your reliability. You really want to pay attention to it and load it the best you can. Now, there is flexibility in sizing the remaining devices in this design. Just at the constraint that the total parallel impedance and the total amount of periphery is correct, right? You need to be at 50 ohms at the end, and that happens when you have the right amount of periphery. So here's an example of estimating those individual device sizes. So I'm going to make that assumption of 100 ohm maximum transmission line impedance, and I'm going to assume the same FET parameters as I already discussed. And then I'm going to go and calculate the device sizes for a 10-cell design at 20 volts. So to get to 100 ohms at that first device, I need to use 800 microns of periphery at this voltage, okay? Now, the remaining devices are quite small on a 10-cell design. You would say, well, maybe if I could get away with 8, that would be better. That would get my sizes up a little higher. That might be a little easier for a lot of reasons. But this is the ideal setup if you assume that you need to get down to that 100 ohm impedance, and then you're going to size the rest the same. So you can imagine, again, now, let's say that I pushed my voltage up to 28 volts, and I needed to get down to that 100 ohms at that first device. That device needs to be a lot larger now. And the larger the device, the hotter the device. And the worse your reliability problem is going to be. So I want you to just keep that in mind as we continue to move along. So now we know kind of how our sizing is going to be at our voltage, at least in this implementation, we need to kind of think about what the drain line impedances need to be. And so you can approximate the drain line impedances. They're defined really by the total periphery of the device, right? And all prior devices in the design. So each one continues to add up with the next as you move down the line. And so again, making the same assumptions, you can go and calculate those drain line impedances for the 10-cell design at 20 volts. And you'll always find at the very end, you need to be at 50 ohms. And so that's what you see. This just cascades down to 50 ohms, and you're at the output and you deliver in 50 ohms. And so this gives you just a good starting point when you're building this all up in your simulator, and you're going to start optimizing, as we'll talk about in a little bit. So the drain line design. So I've showed you how to approximate the drain line impedances shown on the prior slide, which is very straightforward. But you might ask, okay, well, what about the electrical length of each line, right? That's really important. You're designing a distributed amp. How do I set my phases up? Well, this is where some of the art meets the science with a lot of these things. There are some ways of approximating things to some extent, but every design is very different. And I personally find I set myself up with reasonable values of what those may or may not be, and I will end up optimizing them at the end of the day. And I typically start with a linear type simulation of things. I make my S parameters look like they're reasonable, and then I'll go from there with a nonlinear model. And we'll talk about a specific design procedure later, but there's no straight answer for exactly what the phases of those are going to be, because if you think about how many different parameters you could design this with, there's a lot of different combinations of phases of drain lines and phases of gate lines, and what the best possible solution is probably not really defined for every particular design. So that's something to consider. Another constraint you have to think about is, how are you going to use this amp? If you're going to use this amplifier from the standpoint of continuous wave saturated, then DC electromigration is going to be something that's going to need to be constantly at the forefront through your design. You can't just make these lines arbitrarily narrow to achieve the impedance and then assume they're going to handle the current that's going to be drawn through them. You need to make sure that you're always sizing the line for reliability, because you don't want this thing to come back in 10 years. The metal is electromigrated on the line, and then you're in big trouble maybe if you're still at the same company. So it's something to keep in mind as you're designing, that make sure you meet the electromigration constraints of the MMIC process that you're operating within. So you don't have to just make the microstrip line what the impedance is that you end up solving for, right? There's more than one ways to skin that cat. And you can make a transmission line from a microstrip line of a higher intrinsic impedance loaded with capacitors. That is very attractive sometimes. When you start getting into what I'll talk about in a little bit, is where you're designing into a much lower impedance, where it's really hard for me to make a 20 ohm transmission line on wafer in a reasonable set of reasonable space. And so once you start getting to the lower impedance lines, it's really nice to do basically a pi approximation of those transmission lines, where you load that higher impedance line with some capacitors to get the effective lower impedance. Now, you will find once you get to lower and lower impedances, a single section might not approximate it quite well enough. And so you can use multiple sections. But honestly, you can approximate a low impedance transmission line over quite a broad band with this technique. And so it's just something to keep in your back pocket as you're designing these things, or, oh, I need a 20 ohm line and I don't want to make it, hundreds of microns wide to be able to synthesize that. That's just not going to work. So something to keep in mind as you're going through those designs. Gate line design. So the gate line impedance of the individual transmission lines is honestly less sensitive than obviously the drain. And so it's tailorable to some extent. So this is a degree of freedom you can play with when you're designing these things and you're doing your optimizations later. But it's often unnecessary to vary it. There is reasons that you might want to make it a little lower than higher, which I'll talk about in a little bit when we discuss multi-stage design. But it's something that you can honestly tailor for the most part when you're going through the design. The gate coupling capacitors are very important, and you will need them if you want to make something that has efficiency, power, and bandwidth, particularly over a decade. And they are tailored to equalize the drive at each device and maintain a proper match over the entire operating bandwidth. And what you'll always see is that the largest ones are at the end and the smallest ones are at the beginning if you've done it right. If you're going through your design over a broadband and you see that you have one that went the other way, you probably need to optimize your design a little bit more, because they always tend to decrease monotonically as you get back to the very first FET. So largest cap at the very end of the line and smallest cap at the very beginning of the line. So just something to keep in mind. So in this implementation, I've chosen to bias the gates through these large resistors, right? So basically there's this resistive gate line that kind of jumps over all these coupling capacitors. You can hard to see it, but in that implementation, what you really want to do, as I mentioned before, is you make those gate resistors quite large so they don't load the FETs, but you don't want to make them too large because you're going to drive this thing into saturation. It's a power amp, and you're going to start to get some forward gate current. And why a large resistor can be problematic is, okay, you're going to start to get some forward gate current. You're going to draw that through that resistor to the intrinsic gate. So the gate voltage you've set now is at a lower value. And so it's going to tend to pinch the device off. So what you'll do is you'll see power slump back over as you start to drive it in saturation. And so you don't really want that to be a strong impact, but you do want those gate resistors to be large enough to not cause loss in your gate line and degradation of performance. So there's a little balancing act there between, okay, how much leakage am my FET's going to have, et cetera, how much gate current am I going to get when I drive into saturation, and how big can I make them? I mean, if you don't have any gate current, you can make them as big as you want. The final thing you have to design on the gate line is the gate termination resistor, which is shown there next to the bypass capacitance on the gate. And so this resistor functions to basically serve as a load for the wave traveling down the gate line. And so it allows you to get good input return loss at that RFN pin. If you don't have it, then it'll be very reflective, or it'll have waves all over the place, and that would be quite bad. So you do need that gate termination resistor to get a good return loss. And you'll find often that it's typically, let's say if your input terminal is at 50 ohms, it'll be much lower than that. It'll be, I don't know, 10 ohms or something like that, maybe a bit higher, but it'll be lower. And so that's something to keep in mind. Another thing to keep in mind is you're going to drive a lot of power into that resistor, particularly at the low end of your band. At the low end of your band, most of your power is honestly, your input power is being driven into that resistor. And so you need to size that resistor on wafer to be able to handle the power dissipation it has to accept. And so that's challenging because obviously to handle the power dissipation, you need to make the resistor larger. As you make the resistor larger, the less it looks like the resistor that you wanted it to look like over frequency, because it's getting more and more capacitive. So it is a challenging thing to design from a power handling standpoint, but just use a model of that resistor. Typically PDK models exist, which have reasonably good modeling of the changes in the lengths and widths in terms of not just the resistance, but also the parasitics. And so it's just important to not just assume you're going to have an ideal, say, 10 ohm resistor there, because you won't over, say, a 2 to 20 gigahertz bandwidth. Stability analysis is extremely important with distributed amplifier design, as any amplifier design. I'm sure everyone that has done distributed amplifiers or been around them has seen many that have oscillated above band often, typically just above band, because stability analysis wasn't properly carried out through the design phase. And so there are many ways to do stability analysis, and I'm not going to try to sell any of them particularly. I'm just going to tell you what I use, and I typically use loop gain envelope, which is integrated in Microwave Office. And the reason I use this technique is because you can design the stability in as you're optimizing, because it's so fast. What it does is basically it evaluates the contour or the envelope of all of the loop gain circles for a particular device. And so instead of having to swing the source or the input and the output impedance of the device to see where the loop gain circles will go to and am I unstable, well, it just does all that mathematically. and evaluates it. So you integrate it in the loop, you evaluate phase margin, and find out if you're going to be stable. And so you can optimize the phase margin with it. That's what I always tell people, and it's very fast. So if you want to find out more about that method of stability analysis, you can just send me an email, which will be at the last slide, I think, and I can send you a presentation on it. Reliability considerations are massively important with non-uniform distributed PA design. And they're more interesting, I would say, than the standard narrowband reactively matched PA. And we'll talk about more of that in a minute. But basically what happens is, obviously, as you know, that power dissipation has an impact directly on the channel temperature. And the channel temperature of the device defines the reliability of the device. And so what I'm showing on the right-hand side is an example from Qorvo of their MMIC or their GaN processes and what their reliability looks like from a mean time to failure as a function of the channel temperature you operate at. And so as you can see, as channel temperature reduces, reliability goes up greatly, and vice versa. As it goes up, you greatly degrade the channel temperature. And oftentimes people want to have at least a 1e6 MTTF out of their part. And so there's multiple places, though, where reliability can go wrong that you need to pay attention to. MIM capacitors are one place. Everybody is likely seen as a MMIC designer at some point or another, a capacitor that's exploded because too much instantaneous voltage got placed across it. So that's something you need to make sure you do. Obviously, always look at your capacitor voltages and make sure you're within the constraints of the process that you're operating in. We already talked about DC electromigration, which DC electromigration is going to get worse and worse the hotter the environment the part is operating in. And then that resistor, we talked about that gate resistor. And those are really the dominant places that you want to take into account when you're looking at MTTF. And as you know, I'll note again, the first device and second device to some extent in that distributed amplifier, Q1 and Q2, if you go back and look at the diagram later, those are going to be the hottest devices. They're always the hottest devices. The last set of devices will be running quite cool. You'll see that. The first two are always the worst. And you just need to make sure that you're in good shape on all of them, but it's likely going to be one of those two that drives you. So how do you estimate channel temperature? This is an interesting problem because you can't make the same assumptions often that you make with reactively matched power amplifier. Every single device in this chain could be operating at a substantially different power, a substantially different channel temperature, and therefore which one drives the reliability at a particular frequency could change, right? Because everything's going to change across this entire stack of devices as a function of frequency and as a function of device. And so this is where you start getting into some of the big assumptions you may have to make with estimating what the reliability is from the channel temperature. So this is the way you do it from a worst case perspective. And so what you do is you have to rely on a simulation-based estimation of the channel temperature from both an electrical and a thermal perspective. So you go and you look across frequency, you estimate the power dissipation in all the devices and all the passive networks across frequency because it's going to change. Obviously, you need to do that at different DC biases and input powers if you're going to care about that as well. So I would say, hey, your max DC bias and your maximum input power are likely the places that are going to drive you. Then you need to determine the percentage of all the power that's going to get dissipated and allocate from measurement. When you measure this thing later, what power was dissipated in each part of that design, and then you need to analyze the channel temperature. Why do you need to do it this way? Nobody's going to go and do a thermal image of your entire distributed amp to find your worst case spot. It's just not going to happen. In fact, you might not even be able to do it. You probably have source air bridges that are blocking the channel from even being able to see it. So really, commercially, you have to rely on simulation of what the thermal stackup is going to be and what your device is actually doing. And so this is a great reason why you need a really good nonlinear model, not only to design the part, but to analyze how reliable it's going to be. So let's talk about a few more advanced techniques with distributed PA design. That previous slides covered mainly the basics of what you need to do. This covers how you may set up a situation where you need more gain. So I need to cascade 2 stages of a distributed amplifier to get a significant amount of more gain. And this is a proposed way to do that, which has been successfully implemented. We talked about the gate termination resistor of a stage and how it's typically quite a low impedance relative to the, at the point where you would drive that stage. And a nice way is you could use that to your advantage to bias the drain of the previous stage. And so what you can do is you can bypass that resistor and you can inject the drain current for the driving stage at that point. So what that current will do is it's going to ride along the entire gate line of that output stage and flow into the previous stage. And so the nice thing about that is the inductance that you need to basically have a choke at the point where it's a low impedance at that gate resistor is much, much smaller than what you would need if you stuck it, say, at the input to the stage, which is an impedance maybe 5 times higher. And so it's a big advantage in terms of achieving bandwidth out of the driving stage, because obviously the impedance you would want to present to a smaller driving stage is just going to go up from what the output stage is. And so your choke problem gets harder and harder as you move back in the design. So this is a really good way to take advantage of the architecture of the distributed amp and the fact that you have those gate coupling capacitors. You just use those and just feed that current down that line. Another thing you need to consider is that what would this look like if I didn't have to deliver power into 50 ohms? What if I could lower the output impedance? Let's just theoretically say that's possible. And so this figure kind of shows what happens in the case that you can do that. I have my standard trace that's in black that you saw before. That's the amount of power I can deliver into 50 ohms. Well, what if I had 12.5 ohms? That's the green trace. So if I have 12.5 ohms, I can deliver a lot more power, right? I can get past 30 watts at 28 volts theoretically. And why is that? Well, I can use 4 times as much periphery, right? So if I can use more periphery, then I can get more power. And if I use more voltage, I get more power, obviously. And it also calculated the ideal first device size, again, in this case, versus voltage. And so what you can see is that, this is the problem I was talking about before. At 28 volts, I need to use past 1 millimeter of periphery. But if I operate at 20 volts, I only use 800 microns. So that's an advantage too. So this is something that would be really nice to take an advantage of is, okay, well, if I have a lower output impedance, I could, say my boss wants me to get close to 10 watts. Before I had to operate at 28 volts or even higher. Well, now I can operate somewhere, around 16 to 20 volts, maybe, just looking at this simple analysis. That seems like an advantage because my devices operating at 16 or 20 volts are going to be thermally far more better, much more reliable than if I was running at 28 volts, where I'm hoping I don't blow things up. So how do you get down to 12.5 ohms, or for that matter, any lower impedance? Well, you have to use a broadband transformer. It's obvious, right? It's easy to say, hard to do. There are a couple different options that, at least I've investigated and had success with. One of them is the Rutherford transformer, which a transmission line version of a basic Rutherford transformer is shown up in the upper right part of the slide. That gives you a 4-to-1 impedance transformation. So that actually gets you down to 12.5 ohms, which is the example I showed in the previous slide. And there's also a trifilar transformer, which is basically the same as a Rutherford transformer with an extra coupled line interconnected in the same fashion. And that gets you down to 22.5 ohms. And so you don't just go put these in microwave office or ADS and assume you're going to plug them in and tune a couple parameters and see that they work perfectly over a decade bandwidth, because that won't happen. But what you can do is you can put a little bit of matching on the lower impedance port often to do a very good job of approximating a broadband transformer over, say, a 2 to 20 gigahertz. And I've definitely implemented both of these types of transformers over a full decade bandwidth. So you can make the assumption at this point that you can do that. You can lower the impedance that you deliver power into, and you can get a higher power, or use a lower voltage for the same power. There's also a method for creating a broadband combiner, which is related to the previous slide. That trifilar transformer is really, really, really close to a 2-to-1 transformation ratio from the high impedance to the low impedance port. So you can consider in your mind, well, let's design it as effectively a 50 to 100 ohm transformer. And let's take 2 of them and we'll just hook the 100 ohm ports together. Now we have a 3-port in-phase combiner that's 50 ohms. That seems like it should work. And in fact, it works quite well. I've implemented this over a 2 to 20 gigahertz approximately, or a little liberal with the 20 gigahertz, as you'll see in a little bit, but you can approximately do that over a decade bandwidth. And so that's a good way to make a really great broadband in-phase combiner that's actually quite small. What you'll find when you design these things, and this is honestly true of the Ruthroff transformer as well, is that the low end part facilitates the need, I would say, of a shunt L series C section at the front end of the low impedance port. Well, that's actually really nice because I needed to have that anyway in my design to get the drain current in. This is my choke now. It doesn't have to be your choke in the case of just using it as a combiner, but in the case of just using a single transformer in an NDPA, it gives you a great opportunity to use that as the choke. So something to consider. So now you're probably like, all right, this is great. How do I do this? I need to go and do this. What do I do? Well, that's something that, you're going to have to use this information and find your own method. But from a basic standpoint, you need to define your performance specifications and you need a nonlinear device model. I mean, don't try to go do this without a nonlinear device model, because you won't actually know what the reliability is, what you end up with anyway, if you don't at least have some prediction that is meaningful. So I've never fully designed one of these without a nonlinear device model, and I don't recommend you do it, but get a good nonlinear device model, because these devices are not going to be, in most cases, very close to your best load that it's typically, that's what the modeling engineer focuses on. I need to nail that load target. It's going to swing all over the place. It's going to go to easily, I'd say 10 dB return loss, even perhaps worse around that load. So make sure you have a good nonlinear device model that predicts the performance as a function of load. That's key. But then you go and define your architecture, do the simple analysis, pick the number of cells, kind of figure out your peripheries, etc. Build this thing up, build something up, put all the transmission lines in between the FETs, all the stuff you need in the schematic, and then you're going to optimize it. Honestly, you're going to optimize it to your performance specifications. You're going to want to use a global optimizer because this thing's a nasty optimization problem, but it's going to get to the place you want it to be probably quicker than you would think. And so giving yourself a couple of days of optimization max, you'll probably be at some point where you start to replace things with more realistic components, get your EM simulations in, and you'll end up with something that works quite well. So that's how I design these things personally, and I think you could be successful doing that too. But certainly feel free to do things in a different way than I have. So now I'll show you some examples of some designs of different distributed amplifiers that I've done, and just to see what these things look like. So this is an example of that multi-stage concept that I mentioned before. This is a 2-stage 2 to 20 gigahertz driver amp that does say 3 watts of power with over 20% efficiency. And so this is your drain line over here, and this is your output. And then this is your gate line here. And you see I've utilized that technique of injecting, this is my choke for my first stage drain. I'm injecting that current along the gate line. So that current is running all the way along here into the output of the first stage. And so that's how I get the current in. It's just a big bypass capacitor here and here, etc. And then this is the driver stage right here. So in, out, it's a compact type layout. This is a 2.7, basically 2.75 by 2.75 chip. Single gate and single drain, so I've tied them together on chip for simplicity because it's a driver, and incorporated ESD diodes in the design. There's an IEEE paper on this you can go and look up. I think I have the references at the end. Here's the measured versus modeled performance. So measured is in the solid and modeled is in the dashed. In this case, I actually got a slight amount more gain than I simulated, which not always makes me kind of happy. Usually it's the other way around. And the return losses did pretty good at matching up. Obviously, you see the higher you get in frequency, the more things deviate. But from the standpoint of covering the 2 to 20 gigahertz band, we succeeded in this case. And go to the power and power added efficiency. So again, solid is the measured, and dashed is the simulated. Pretty close to model performance. So the nonlinear model did a pretty good job. Particularly the higher you go in frequency. Lower is a challenge, because if you consider it, there's a lot of harmonics in band. You know, if you're running this thing at 2 gigahertz, your 10th harmonic is still in your bandwidth. It's very different than what a lot of designs often have, right? So it is challenging to model this power added efficiency as well as it ends up being because of the harmonic contributions. But in general, I mean, nobody's going to be upset if your efficiency went up. Here's an example of a higher power GaN distributed amplifier that uses a transformer concept. So this used a broadside coupled roof-off transformer, which is 0.2 down here. And again, drain line to the transformer, the last FET, and then you have some matching that's added to improve the low end performance. Do the same thing with the running the bias of the first stage, that drain bias along the gate line, feeding it to it. And then you have a several cell driver stage. And so single gate connection in this case tied them together because decided to bias them at the same point. I separated the drain voltages because it worked well with the layout and minimizing the size. So this chip is not that much bigger than the driver amplifier, right? 3.24 by 3.24, but it's effectively almost 4 times as much power. Here's the measured versus model. So in this case, I got a little bit less gain, probably because the devices are larger and it's running a little bit hotter. But in general, covered the 2 to 20 gigahertz band, which is fantastic for a 10-watt amplifier. Return losses are in decent shape across the full band. So all in all, pretty close to model. Here's the power and power added efficiency. So it held 10 watts, 2 to 20 gigahertz. I mean, it's at 10 watts effectively at 20, and it's above 10 watts, obviously lower in frequency. And the efficiency held up, didn't beat 25%. So I'm not a hero, but it stayed above 20 for the whole band. So that's a pretty good performance for a 2 to 20 gigahertz amplifier. And here's the performance over temperature. So it just doesn't, this is just to prove it doesn't totally fall apart. The red traces are 85, blue traces are -40. So you can see the degradation you see over temperature. The better thermal environment you can put a distributed amplifier in, the better it's going to perform. So this is measured on a copper moly carrier plate. But if you can use copper diamond or some diamond exotic tab out there with the best die attach possible, it's just going to get better. So something to consider if you want to spend your money on something that's going to directly lead to performance, improve your thermal environment. Final design that I'll show, this is using that combiner that I discussed. You can see these little alien looking things here in the middle. It's a splitter and the combiner. And you just basically take two designs and combine them. It's a giant chip. It's almost 7 millimeters tall, but it gives you effectively 20 watts across a 2 to 20 band, which that doesn't happen, right? That's a tough problem. Here's the measured performance of that design. So from an S parameter perspective, effectively held 18 dB plus gain with that 2-stage combined design across 2 to 20 with good return loss. Power started to slump though. Combiner loss was getting a little high on the edges. And so it holds 20 watts from 2 up to 19, I'll say, and then it dips below that by half a dB at 20. Power added efficiency, you see that impact on the loss up to the high end. So, it's dropping below 20% at 20 gigahertz, but stayed above 20%, up to 19 point something. So pretty decent performance for a decade bandwidth amplifier. So in conclusion, shown the basics of NDPA design. So hopefully you can use those to start a design if you've never done one. Maybe you learned something as a distributed amplifier designer that you could use in what you're doing today. But go forth and conquer. Try something new. I mean, we never do anything new if we don't try something new. So make sure you take what I've shown you and do something different maybe. It's very advantageous to apply that drain bias to the driver stages through the next stage's gate line. That's a concept that's highly useful because it's a good spot to put a choke. The choke works better when it's attached to a lower impedance point in the circuit. You can use transformers to increase the power rather than simply pushing the drain voltage up. And prior to a few years ago, people were just trying to get the maximum power by pushing the voltage as high as the foundry would let them. That's not necessarily the best way to do it. There's circuit techniques that allow you to do a better job over a restricted bandwidth. Sure, if you're doing DC to daylight frequency, you can't do that, right? You can't make a transformer that works over 100 gigahertz, at least as far as I know. But let's say you have a decade and it's 2 to 20, and you can do it. Showing out how to do that. I've also shown how to make a decade bandwidth combiner and how that's possible to increase the power further. So that's another thing to investigate. There's probably many other things that haven't been thought of, I'm sure. So just go and investigate different options and see what you can come up with. Here are the references with some of the papers that have those mimics in them. They've already been published. And thank you. If there's any questions, feel free to ask.
Thank you so much, Mike. That was a very, very good presentation. I am seeing a lot of wonderful comments in the webinar chat. A lot of people are liking the PA performance that you showed. Let's